For some random variables, it's impossible to write down all the possible values that they could be. For example, say we wanted to measure birth weights on babies or life expectancies of countries, and we wanted to measure them to any number of decimal places. It would be impossible to write down all the possible values of the birth weights or the life expectancies. And if we wanted to assign probabilities to all the possible values, it would be impossible to again write down what each probability would be for the possible values of life expectancy or birth weight, since we can't write them all down. In this situation, we have to rely on a mathematical model for the probabilities. And in this video, we'll consider the idea behind how to construct such a model.
A random variable takes each outcome from a random experiment or random process, such as flipping a coin or spinning a roulette wheel or measuring the birth weight of a randomly chosen baby, and it gives that outcome a numerical value. We say a random variable is continuous if the numbers it can be are anything within an interval, where the interval can extend as low as -infinity all the way to +infinity, or it can have finite bounds. Here's an example. Suppose buses arrive at a bus stop every 10 minutes, and we want a probability model for how long a rider has to wait for a bus when they arrive at the stop. If we don't know when the last bus arrived, perhaps a good model for this would be a model that makes it equally likely for a bus to arrive at any time between 0 and 10 minutes. We could illustrate the probability of the bus's arrival with this line over the interval from 0 to 10 minutes, since those are the possible arrival times. And we'll make the line horizontal because the bus is equally likely to arrive at any time in the interval. Now, since the interval is 10 minutes long, the probability the bus arrives in the first minute should be 1/10 or 0.1. We'll represent that probability, the probability that the bus arrives in the first minute, as the area under our horizontal line from 0 to 1 minute. For the area of this rectangle to be 1/10, which is what we want because that would be the probability that bus arrives in that first minute, then the height of this line must be 1/10 or 0.1. This model for the arrival of buses is an example of a uniform distribution for a continuous random variable. We'll call the random variable x, and x stands for how long a rider has to wait for the next bus. X has a uniform distribution on the interval 0 to 10. And we write this as x tilde, meaning x has the distribution, uniform because it's a uniform distribution, and then we put the range or the interval on which that uniform distribution holds in brackets from 0 to 10, 0, 10. X is a continuous random variable since it can take any value in the interval. So this is a continuous uniform distribution. This horizontal line that we've drawn from 0 to 10 at height 1/10 is an example of a probability density function. Here's a little cleaner version of the probability density function for the waiting time for the next bus. Probability density functions are mathematical functions to describe the probability distribution of continuous random variables. A probability density function is a curve that must satisfy two conditions. It must always be greater than or equal to 0. We can't have negative probabilities. And since the probability that something happens is 1, the total area under the curve must equal to 1. When we sketch a probability density function, we have the values the random variable can be on the horizontal axis and the value of the density function on the vertical axis. What's of most interest in this sketch of the density function is the areas of regions underneath the function. Probabilities for a continuous random variable are found by finding areas under its probability density function. The probability that a random variable falls into any particular interval is the area under the density curve above the interval. For example, suppose we want to know the probability that our rider waits less than 2 minutes for the bus. We find the area under the density curve from 0 to 2, which is the area of the rectangle with width 2 and height 1/10, and so the probability that x, our waiting time, is less than 2 is 2/10. The probability of waiting between 2 and 6 minutes is the area of this rectangle with width 4 and height 1/10, and so the probability that x is in between 2 and 6 would be 4/10. And we can verify that this is a valid density function because the total area under this curve is 10 times the height of 1/10, which is 1, which is required of all density functions. Although this might seem counterintuitive, the probability that a rider must wait exactly 2 minutes for the bus is 0. Here's why. If we try to find the area under our density curve for a wait time of exactly 2 minutes, the area would be 0 because we have 0 width. For any continuous random variable, the probability that it is equal to any one particular value is always 0. You can think of this as getting that one particular value out of the infinite number of possibilities in the interval that the random variable can be. So any one particular value is just 1 out of infinity and has probability 0. As a result of this, for any continuous random variable x and a numeric value a, the probability that x is equal to a is 0, and in turn, the probability that x is, say, less than a is exactly the same as the probability that x is less than or equal to a. Density functions can have many shapes, not just uniform. The language used to describe them is the same language that is used to describe the distribution of data. Density functions can apply to probability distributions that are uniform or symmetric, maybe bimodal, could be right skewed, and so on. The key for any density function is, again, that the total area under it is 1. And for a random variable whose probability is modeled by that density function, the probability that the random variable is in an interval is the area under the density curve. Here's another way to think about the concept of a probability density function. Suppose our bus rider recorded how long she waited for a bus for each of her last 200 rides. We could picture these data in a histogram, showing the frequencies, that is the counts, of how many times she waited between 0 and 1 minute and between 1 and 2 minutes and so on. Now, if we change the scale on the vertical axis so that the total area of all of the rectangles in the histogram is 1, we get a density histogram. Areas under this scaled histogram give the proportion of wait times that are in any interval. For example, the area between 8 and 10 minutes is a total of about 0.115 plus 0.10 or 0.215. So then we can use these areas to estimate that the probability that our rider waited more than 8 minutes is 0.215 or 21.5%. We could approximate this density histogram by a smooth curve to capture the overall shape of the distribution of wait times. Smoothing this density histogram gives us a mathematical model for the probability density function for our bus riders' wait times. And that smoothed curve would be the uniform on the interval 0 to 10 probability density function. That is a horizontal line that is at height 1/10 and ranges from 0 to 10. We could then use this model to estimate the probabilities that the wait times are in any interval. In this way, we're thinking of our data as actual observations of a continuous random variable, and the probability distribution of this continuous random variable is described by this probability density function. So the probability density function is a mathematical model telling us how individual observed values of the data behave in terms of the probability that an individual value is in a certain range. Let's look at another example. The birth weight of a baby is another continuous random variable, but it won't have a uniform distribution. Here is a histogram of the birth weights of 200 male full-term babies at a hospital. Again, let's change the scale of this histogram so that the total area of the rectangles is 1. This gives us an approximation of a density function to describe the probability distribution of the birth weights of these babies. This distribution has a familiar shape. It's symmetric, unimodal, and bell-shaped. Approximating the shape with a smooth curve gives a mathematical model for the probability density function of birth weights. And in this case, it would be well described by a bell curve. Again, this smooth curve is a density function. Probability density functions with this shape are very common. And in many situations, as is the case for these birth weights, they can be described well by a family of density functions called normal densities. Mathematically, this probability density function is much more complex than a uniform density function, but probabilities are calculated the same way, as areas under the density curve. So, say we wanted the probability that a male full-term baby born at this hospital had a birth weight between, say, 4,000 and 4,500 grams, then we'd find the area of this shaded region.
Observations of a random variable whose probabilities can be described by a normal density are said to follow a normal distribution. The normal distribution is extremely important in statistics, so it will be important to learn more about it going forward.